In this course, we are going to learn about databases. The computer science is not only about algorithms, but also about data that is processed by those algorithms. When we have too many information, we need them to be stored in an ordered manner, and in the 70s, some computer pioneers thought about what is the best way to create order in that chaos of data. As in other domains, we need to be able to verify ourselves that what we are doing is indeed correct. Also, as in other domains, we are going to use mathematics and logics that are probably the best way to verify something, by building its mathematical model and verify if that model complies with some restrictions and properties that we need to have in the system. In the first course, we are going to introduce the relational algebra that was built by Frank Edgar Code in the first year of the relational databases. We are going to continue in the following courses with some properties of the databases, functional multi-value dependencies, and how they are important in the process of normalization, process that is going to be explained in the last two courses. The relational algebra consists, as any other algebras out there, from a set of elements and some operations that are defined on those elements. In this case, the elements are some tuples, meaning combination of values. So each element in this algebra is actually something like a record in C++, contains more than one value. Let's see how to formalize them. Consider a set U of attributes A1, A2, and so on. For example, in our laboratory we have a set of attributes that are registration number, first name, last name, year, scholarship, or the date of birth, that are actually the property of a student. Each such property has its own domain. For example, the names are strings, or the scholarships are numbers. So each attribute has its own domain from where some values can be associated with that attribute. This association is made by this function phi, considered here, that is defined over the set of attributes, and when applied to an attribute, it will give us the value that is associated with that function by that function phi to the attribute. For example, we can consider such a function that when applied to an attribute, last name, will return the string Morrison, and when applied to the first name, will return the name Cody, and so on. Of course, we are considering more than one single function, but we will see about that in a few moments. For now, let's consider that the function phi that is defined here, when applied to the attribute A1, will return the value V1. When applied to the attribute A2, will return the attribute V2. And so on. Because we have more attributes and the functions return a value for each attribute, a value that is from the attribute domain, we can make a direct association of the value with the attribute. We will write it like this. Into a bracket, we'll put A1, 2 points, and V1, and so on. We need to always write the association because the tuple, as is defined here, is more like a set of elements, and the set don't have a certain order, unless it's specified, and we didn't specify one yet. It's pretty simple to define an order on the attributes when we build a table. In the creation sentence, we introduce the attributes in a certain order. Considering that order, we can write the values in the values in some order as the attributes, the same order as the attributes are. This way, we can actually write something more like a sequence of values, as it is written here. So v1, v2, vn, that are the values that are associated by the function phi with the attributes a1, a2, an. For each ordered set of attributes, if we consider a function phi, then we will obtain an ordered set of values. So tuple phi, we will obtain the set of values. And also for each ordered set of values, each from the domain of the corresponding attribute, we can define a function phi such that the function phi, when applied to an attribute ai, will return the value vi that should be associated with the attribute ai. In SQL and in the rest of the course, we will always consider that the set of the values are ordered in some order, the same as the attributes, and the same order that is used when creating the tables. Okay, we define a function phi, but that function only gives me the single set of values, of order values. If we define a second function phi2, we can obtain a second sequence of values, and after that we define a function phi3, and so on. As we could see in the previous slide, the function phi and the set of values returned by the function are one and the same. They can be built one from the other. That is why in the rest of the course we will get rid of the function and will actually consider only the ordered set of values. But there are many ordered sets of values for each function, and we need to create a set of such tuples. This set of tuples is called a relation. The relation is built on the set of attributes u, meaning that all tuples in the relation have to have the values for the attributes in u. So for the first tuple, we will index its values with the two values. For example, here we've got v11, v12, v1n. The first index here shows us the number of the tuple. This is the first tuple. And the second parameters, the second index, tells us what attribute is associated, this value should be associated with. So this is the attribute, the value for the first attribute, for the second attribute, and so on. This is the second tuple. As you can see, the first index it's now 2, and so on. Even though we consider the values here, the values are not that important when we study the databases, if the database is correctly built. More important than the values is the relations between different attributes, and if some values could be in some context obtained from the other values. That would mean that we have some types of redundancy in the database, and we don't want that to happen. That is why we need to normalize our databases. In order to normalize the databases, we will use the attributes, the schema of the relations. You can think of the schema as being a definition of the database, or the schema of the database. For example, a schema for a relation R, it's denoted by R and U in squared brackets, and where R is the relation name, as we can imagine, that is the table name actually, and U is the set of attributes, and that actually means the names of the columns. So for example, RU might be students. This is the name of the relation, and the attributes might be ID, name, and scholarship. And usually when we create a table, we also define the domain of each attribute. For example, the ID, it's an integer. In practice, the tuples are written one under the other, and that is why we obtain a matrix-like representation. Let's see it actually in practice, and I will use Oracle interface, command line interface, to display, for example, the students that are in the table students in our laboratory. For this, we will run the command, the SQL command select everything from students. And we can see here that I find all the students. There are 13 students. Each student has an attribute registration number, an attribute last name, first name, year, group, scholarship, and the date of birth. So those are the attributes from where our relation is built, and our relation actually contains the values that are here in the table, in this matrix-like representation of the relation R. A database schema is actually composed from different table schemas. So a database schema is a set of all the relation schemas, and if we consider the actual relations that contain information in them, like the table I've just shown you, we will obtain the database, the entire database. So a database over D is a projection that associates a relation R to each relation schema in D. For example, we can consider if I have H relation schema as here, R1 of U1 and so on up to R hash and U hash, then the relation should be R1, R2 and R hash. Let's now see what are the operations that can be used in the relations. Keep in mind that the relation is a set of tuples, matrix-like looking, and the operation that we are going to define is on that kind of elements. These are the operations in the relational algebras, where the result of an operation is always a new relation. Because the operators are sets of tuples, we can think about the first category of operations as being the operations from the set theory: the union, the intersection, the difference, and the Cartesian product. Some other type of operations are relational algebra specific operations like projection, selection, or different type of joins. Let's see each of them in detail. The first operation, but let's now make a small parenthesis. When we're talking about union, intersection, and the difference of two relations, we have to be very careful. Both relations have to be built on the same set of attributes. Otherwise, what could be the attributes in the result? For example, we cannot make the union between the relation named students and the relation instructors because the tuples in those two are not compatible. The union of two relations R1 and R2 is the set of tuples that are either from R1 or from R2. Of course, the result is built on the same common schema of the two relations. In SQL, the union of the two relations is obtained by using the keyword union, and let's see now an example. We can obtain all the students from the first year and the third year simply by reuniting those two selects. So we are going to write here the SQL command that will give us all the students from the first year. Select everything from students where year equals 1. For example, those are the students in the first year. Those are the students in the third year. And if we want to see all of them, the one and the third, the one that are in the first year and the ones that are in the third year in the same result, we can do something like select everything from students where year equals 1, union, and select everything from students where year equals 3. And now we will see that we'll get all the students that are in the first or in the third year. The second operation that we can obtain from set theory is the difference of two relations R1 and R2, both over the same set of attributes, again, over the same set of attributes always. Is a relation denoted by R1 minus R2 and is defined as being the set of tuples T, where the tuple T belongs to the first relation R1 and at the same time the tuple T does not belong to the relation R2. In SQL, this is obtained by using the word minus. So let's try to eliminate all the students that have scholarship from the set of students from the second year. We will select all the students that are in the second year and we will remove all the students that have scholarship in their scholarship field. Okay, let's first see what are all the students that are in the second year. We can do this by running this query. So as we can see, the students that have scholarship are only Ortega, Susan, and Clark Nicholas. Let's check all the students that have scholarships. For example, we can do this by selecting students where scholarship. The scholarship is not null. It means that it has a value there. As you can see, the Ortega, Susan, and the Clark Nicholas, they are some of the students that have scholarships. They are the only students in the second year. by making the difference between the first set of the students that are in the second year and the students that have a scholarship, we will obtain all the students that don't have a scholarship from the second year. So we will obtain Keller Jane, and again Keller Jane. There are two students that have the same name, but they are different students because, as we can see, they have different registration numbers, and they are actually in the different groups and have different birth dates. So let's do this. I will select everything from the second year. I will remove now everybody that have a scholarship, and we will obtain the two Janes that don't have scholarship from the second year. Another operation that is used from this set theory in our databases is the intersection of two relations. The intersection is denoted by R1 intersected by R2. Both R1 and R2 have to be over the set same of attributes U, and the intersection is formed from the tuples that are in both R1 and in R2. This is the logical end. In SQL, we can obtain this by writing the keyword intersect, and I will let you to test it out, this command. Okay. Let's check the last operation that is available in SQL from the set theory, is the Cartesian product. In the case of the Cartesian product, the two relations involved have to be built over two different schemas. It is mandatory in this case that the set of attributes from the first relation schema has nothing in common with the set of the attributes in the second schema. The intersection here is the empty set. The Cartesian product happens as in math. The first row from the first relation is associated with each row from the second relation. The second row from the first relation is then associated with all the rows from the second relation, and so on. If we take a tuple from the result and consider only the values associated with the attributes of the first relation, then we will obtain a tuple from the first relation. This is actually an operation that is called the projection of the tuple T over the set of attributes from U1, and they have to be from the first relation. Also, in the same time, if I'm projecting the tuple T in the result over the set of attributes U2 from where the second relation was built over, we will obtain a tuple from the second relation. In practice, the two relations have, even though that we said that they have to be different, in practice actually always we have different type of columns there, because if they are the same, they can be prefixed by the name of the table followed by the dot, followed by a dot sign. So we will try to make some Cartesian products between the students and the professors. In Oracle, this command is specific for Oracle only. We can add a comma between the two tables from where we want to have the Cartesian product. In SQL standard, we will use cross join these words between the two tables that are involved in the obtaining the Cartesian product. So let's check those. For example, we can do select everything from students join the teachers, profs. Not join, but it was the first example. It was the simple comma, and I will obtain all those representation. Let's do some commands for altering the settings in this SQL Plus application. I will add set line size of 140 characters and set, and let's execute again the command here. This is the Cartesian product from the students and the teachers, and I will have 182 rows. Okay, as you can see, Maxwell Gloria, that is one of the students, is associated with all the teachers that are here written from the table teachers. As you can see, for example, Herbert Dustin here also was associated with Christo Robert, and Cash Hugh was also associated with Christo Robert, and so on. So this is a Cartesian product. We can check that it is indeed a Cartesian product by looking at the number of elements in the first set and looking at the number of elements in the second set, and then the Cartesian product should have the product between the two cardinals that we found. For example, if we look at number of the students, we obtain that there are 13 students, and teachers, there are 14 teachers. If we multiply 13 by 14, we will get 182. Okay, I said that in Oracle it's this comma, but in SQL standard we should use cross join. This will get the same result, the same 182 rows, and also Christo Robert is associated with each student in our student table. We need to have some operations to manipulate the format of a tuple, or that select some certain tuples, or that associate a tuple from a relation with the one from other relation. These are the relational algebra specific operations and will be described in this section. The first operation is the projection. This operation helps us to obtain only some values in a tuple, not all of them. For example, I might be interested only in the name of the student and if it has scholarship or not. It's useless in this case to also get the date of birth or the year of the student. So let's now consider a relational schema RU and a subset of attributes X that is included in U, and T is a tuple over this relational schema. So it belongs to a relation R, this tuple T. It is called the projection of the tuple T with respect to the set of attributes X, and is noted by Px of T, the restriction of T of the tuple T to the set of attributes in X. What does this restriction mean? It means that we will only take the values from the tuple T that are associated with the attributes that are in X. Of course, the tuple T contains a value for each attribute that is in U, because this is how the relation R was built. T belongs to R, so T has to be over all the attributes in U. And X being a subset of attributes, then we can T will contain the values that are also associated with those attributes. We'll only obtain those values in this projection. So in this example, we have a set U of n attributes, A1, A2, and so on up to AN, and the tuple T that is formed from the values that are associated with those attributes. Consider now a subset of X of attributes, a subset of U. Those attributes are denoted by A, I1, A, I2, and so on. Why did I create a number with the index? Because this shows us that it's not really mandatory to select the first attribute. A1 here might be, for example, number 2, or I2 might be, for example, the attribute number 5. It is important those number I1, I2, and Ik have to be some values between 1 and n, because we only have attributes from 1 and n to n. Then the projection of the tuple T with respect to the set of attributes from X, it's formed only from the values that are associated with those attributes in X. So for example, Vi1 is associated with AI1, Vi2 is associated with AI2, and so on. Of course, if we can extend this tuple projection to a set of tuples, to many tuples. So we can think about projecting a relation, the entire relation, with respect to with respect to a set of subset of attribute X, the subset or subset of attributes from U. So if R is a relation over RU and X is a subset of attributes from U, then the projection of R with respect to X is formed from all the projection of each tuple that is in R. For example, let's consider U as being A1, A2, AN. Then R might be, for example, formed from M tuples V11, V12, V1n, and up to the tuples number M, VM1, VM2, and VMN. And if I consider X a subset of attributes from U, then the projection of the relation R with respect to the set of attributes in X is going to be formed only with those values that are from each tuple, but that are on the position on the same associated with the same attribute here in X. For example, V1 I1 is associated with AI1 here. This is associated with the second one. V1 IK is associated with A1 with AIK there. In practice, in SQL, the projection is achieved only by selecting some columns in the table. And let's see an example by selecting only the first name and the last name from the table students. Let's do this. Select So I obtained the projection of the tuple, or of all the tuples in the relation students, over the first name and last name. Okay, let's continue with some other operation. This is the selection. Okay, this is some other example that you can test by your own. For example, we can make now the union between the names of the students and the names of the teachers, because they are now compatible one with the other. The second operation that is specific to relational algebra is the selection. It is denoted by sigma. But before explaining exactly what sigma means, we need to understand what a selection expression is. And for that we will define the elementary selection expression as being a Boolean relation between two attributes. But actually, when we are going to filter a table, we will obtain only those tuples that have the values associated with A1 in this relation theta with the attributes in A2. So for example, if I'm trying to get all the students that have the first name bigger than the last name, this is something that is not really actually a natural query, but might be a lexicographical order. Then we can do something like select everything from students where first name is bigger than last name. So this relation between two attributes might be used in selecting only those tuples that actually respect this condition. So this condition might be, as I said, an elementary selection expression that is between two attributes, or might be between an attribute and a constant, or between a constant and an attribute, where, as you can see, A1 and A2 are two attributes from set. After that, we can create more complex selection expression by using the logic operations. For example, if phi1 and phi2 here are selection expressions, elementary or not, then the following are also selection expression. So phi1 into round parentheses, not phi1, phi1 and phi2, phi1 or phi2. Of course, we write this in relational algebra, but actually there are keywords that allows us to do this logic operation in SQL too as well. So if semantically speaking, if phi is a selection expression, consider that, for example, phi it's a selection expression between two attributes. It's a basic expression. Then a tuple T will satisfy this condition if the projection of the tuple T over A that will give us a value, it's in the relation theta with the value that is obtained from the same tuple, but when projected over the attribute B. So here actually for each tuple we will compare the values that are existing in that tuple, and if those values are in some relation, then the tuple will be considered in the answer of the query. Here is, for example, a attribute compared with a constant, or a constant with an attribute, and if we did something like logic expression in this selection expression, we can consider that if phi is not phi1, then T satisfies phi if T does not satisfy phi1, or if phi is the conjunction between phi1 and phi2, T satisfies phi if it satisfies both phi1 and phi2. If it's OR here, the disjunction, then T will satisfy phi if T satisfies either phi1 or phi2. Then if phi is a selection expression, then the selection phi over the relation R, denoted by sigma and phi here is the condition, over the relation R, is defined being the set of tuples that are built from over the RU. So it's from the relation R here. R is built over the RU with the property that T satisfies this condition. In SQL, in this language, we can do this by using the keyword where. And for example, I have here a selection of all the students that are in the second year and also have the scholarship null value. Those are, I think, the two Janes, the killer Janes. Okay, so in this case, this is elementary expression selection. This is also an elementary expression selection, and this is the conjunction between the two elementary expression selection. So it's a more complex expression selection. Let's do this in SQL to test it out. So select everything from students where year equals 2 and is null. Actually, as I said, there are here we can find those two Gauss killer Janes. Third specific operation that is specific to relational algebra is the renaming. The renaming is very useful when we want to alter the name of a table momentarily, not for real, or when we want to modify the name of the attribute. For example, we don't want there to be called the attribute to be called, for example, first name. We can want to, for example, to say something like surname or family name, or I don't know, something different. For example, we can rewrite the scholarship into money. What money that students have. Let's try to do this rename, and we will get in a moment to this operation natural join. For example, here we can try to rename the scholarship into a column that is named $$$$$, $3. Okay, so select first name, last name, and scholarship as, and we can write here $3 from students. As you can see, the alias is written using double commas, not double quotes, not the single quotes as usually it's written in SQL. And this is, I think, this the only area where we can write double quotes. It's, I don't know, it's the only part in the command that we can write double quotes here and in when renaming. So I will rename now the scholarship into $3. As you can see, the column here is called have $3 there in the name. Going back to the theoretical part, let's see what is the fourth operation that is specific to the relational algebra. I think this is one of the most important operations that are in the databases, is the join, and in this case is the natural join. Why it's important, this join, is because usually when we normalize databases, it means that we are going to decouple some information. For example, even though I know, for example, that a student has different grades, I'm not going to add the grades of the student in the same table as the student, because this might create some redundancy. For example, if a student has the grade 10 for the databases, and also the same student has the grade 9 for some other course, for example mathematics, then if I'm adding all of them, all those information in the same table, for each mark, for each grade, I have to rewrite all the information, all the data about the student. So the student is going to be the data about his about the student's like first name, like last name, if it has scholarship or not, what is his year on, and so on, will be written twice. That is why we are going to try to explode something like this, this information into many tables. For example, I will have a table specific to the students, a table that is specific to the grades, and also one that is specific to the type of courses that in where describes each course what it's about, and what it's its title, how many credits we have, when it's taught, in what year and what semester, and so on. And when we have this information distributed over different tables, we want sometimes to get them back together. So, for example, I want to know what are the grades of a certain student. This is done with this operation that is called join. The first type of this operation is the natural join, that associate the rows between the two tables based on the attribute that is common to those two tables. Okay, the name of the attribute counts now this time, because if we have the same name in both tables, that is the attribute that is going to be used. Let's consider now the theoretical approach, and after that we'll give an example and also write some commands in our SQL interface there in SQL++. Okay, let R1 be a relation over the set of attributes U1. It's the schema, it's R1 of U1. R2 is a relation over R2 of U2, and it is called the natural join of the relation R1 and R2 is denoted by R1 join R2 over the set of attributes, the union between U1 and U2. As we can see here, the intersection is not specified if it's the empty set or not, but if it's the empty set, then we will obtain the Cartesian product. Okay, so over the set of attributes U1 reunited with union with U2, and the join of the two relations R1 and R2 is the set of tuples T over the set of all the attributes in U1 and U2, so the union of those two, such that when I project this tuple over the set of attributes U1, I will obtain a tuple from R1, and if I'm projecting this tuple over a set of attributes U2, I will obtain a tuple from the second relation R2. Sometimes when I'm writing U1 reunited with or union with U2, I will write it by like this, U1 and U2 without the union sign between them. Let's see an example. For example, if I have two relations R1 and R2 that are built over the schemas R1 of A, B, C, D and R2 of C, D, E, as we can see, the common attributes here are C and D. Now, when I'm trying to make the join, I'm trying to make something like an association between a row from the first relation and a row from the second relation, such that when I'm projecting over the A, B, C, D, I will obtain the row from the R1, and when I'm projecting over the C, D, E, I will obtain the row from the second relation. In this case, let's take the first row here, 0, 1, 0, 0. I'm looking at the C and D attributes. They have both 0 as a value on them. If I'm looking at the second table, I'm looking for all the rows that have 0 and 0 for the attributes C and D. And this is the third row here. So I will associate the first row with the third row, and I will obtain the first row from the result, 0, 1, 0, 0, this one, and also 0, 0, 0, that is actually the row from the second relation. Let's check now if we don't have any other rows that can be associated with the first row. As we can see, there are none other rows here in R2, none other tuples that have 0, 0 on the attributes C and D. Going to the second row, we'll proceed the same. So I will look in the second table for all the rows that have 0, 0 on the attributes C and D. And now I will obtain the row that is 1, 1, 0, 0, and 0, 0 can be continued here with another 0 from the E attribute. So I'll have 0, 1, 0, 0 and another 0. 1, 1, 0, 0 and another 0. Going to the third row, I will try to find all the tuples there in R2 that have 1 and 0 for the C and D attributes, and I will obtain, this time I have two tuples here that can be associated with the third tuple in R1. So I will obtain 0, 0, 1, 0 and 0 for the last attribute E, or 0, 0, 1, 0 and 1 for the last attribute there, E. In SQL, if I'm trying to do natural join, this is done by using the expression natural join, and let's try to find all the values of the grades that are from that each student have. I will select only the last name of the student, probably the first name might be also selected, and the value of the grade. Okay, let's do this. Select last name, first name, and the value of the grade from student, natural join grade. And I'll obtain 42 rows for each student that has a grade. For example, Morris and Cody have those grades, 8, 9, 10, 9, 7, 8. I didn't want to find also the name of the courses where he has, for example, 10. He is the best student at that course, but only the grades. There are only 42 grades that are now associated with the person that took that grade. Let's test if indeed we have 42 grades. And indeed we have 42 grades. And the association field, the one that is used for the natural join, is this registration number. That it's a common field on both grades and student tables. If I'm describing the table students, I have this registration number. If I'm describing the table grades, I have again registration number. We will see that natural joining is not useful in not very useful in practice. Some companies don't ever use this natural join, and this is because when I'm creating natural joins, I'm also having all the attributes there. So for example, if I'm trying to obtain all the, not only the names and the grades, as I did here. I want also to find out what are the names of the courses. The name of the courses is the let's see the table courses to see what are the fields there. So the course title. If I'm trying also to obtain the course title, and I can do here natural join courses, I will obtain nothing. It will not give us an error, so the SQL command is okay, but I will have no row selected. Why is that? This is because when I'm doing the first natural join, I will obtain also an attribute that is called year. This attribute year is the year where this student is registered, where it's what is his year, in what period of his career of as a student is there. So is the first year, the second year, or the last year. And also I've got here a field that is called year in the course, meaning the year where this course is taught, or the semester where this course is taught. Okay, so those two are not compatible, and that's why I don't have any no row selected, because this join contains indeed the ID course, the field that I wanted the natural join, the second natural join, to be to look at the common attribute, but it also this natural join also looks like the second common attribute, that is the year, that is now present here in this join, and also is present here in this courses table. Okay, in order to do this, I will have to write some different type of join, and this different type of join is called the theta join. I had something like some properties there, but they are not. Maybe I will come back to them later. So in order to do this operation, where I want to find, when I can find also the name of the course, I will consider a different type of join that is called a theta join. As you can see, the theta is a condition that can be applied between the attributes, or between the attributes and the value, or and so on, and or can be formed with the condition that is a more logical condition, and will be selecting only the tuples that can be associated one with another based on this theta condition. So if I have two relations R1 and R2 over the two different schemas, and they have k attributes, a alpha 1, a alpha 2, a alpha k, and b beta 1, b beta 2, and b beta k. So I will build such a theta condition here, the one that is used from theta join, by having k theta I, k small theta, let's say, conditions over the domains of the attributes from the first relation and from the second relation. So and the tuple will be, it's actually something like a Cartesian product, that it's considered in the output, in the result, only if the projection over the attribute a alpha 1 of t1, it's in the relation theta 1 with the attribute with the value obtained from the projection of t2 over the b beta 1 here. Okay, this is the expression that tells us where is the selection made over the when the two T1 and T2 are associated. Many times we use this condition theta 1 and theta 2 as being the equality, and in this case this condition theta is called it's only with equalities, and the theta join is actually it will be called equijoin, and that's what we are going to use to also be able to add the title of the course. Let's try it. Select actually I will correct only this one. I will remove the natural join, and in this theta join that is between students in this AQ join, I also have to write the condition of the join, and the criteria is on students dot registration equals grade okay, and I will add here join courses on grade equal courses dot id course. Student register, I made a typo there. Registration number. So now I'm having the name of the student, the grade that he obtained, and the title of the course where that grade was taken. Going back to the natural join, this natural join have some properties. For example, we can see that if I'm doing the natural join of the two relation R1 and R2 and I'm projecting over the set of attributes U1, I will obtain actually the tuples that are used from the relation R1 to in the natural join, to create the natural join. And the second is, and the same is for the second tuple, for the second relation. If I'm projecting this natural join over the tuples U2, I will obtain those values that are used in the relation from the relation R2 that are used in the natural join. If we have x as an intersection of between U1 and U2, then we can consider that projection of over the x to be the joining condition, and I'll consider here R1 to be the tuples T1 from R1, such that there exists a tuple T2 in R2, such that the tuple T1 when projected over X, I will obtain the tuple the same values as the tuple T2 projected over X. Okay, so this is something like this is the first set here. Actually tells us what are the tuples from R1 that are used in natural join. It means that they have something in common on the set of attributes X with the second relation. Also, we will consider another relation here, R1 second, being the lines that remain. For example, the lines that are from R1, but they are not used in the natural join. It is remaining lines. This in SQL it's a little bit trickier because there is no command here to obtain the first one is the semi-join. The semi-join is from the lines where that are used in the natural join. Let's check, for example, what are the lines here in this natural join. For this one, the easiest way is to also add here the year of the student. Now, in the result, I will have two fields that are called year. Okay. If I'm writing this, I will obtain an error because the SQL does not know what field I'm referring to, the one from the students or the one from the courses. So I will obtain an error. But it tells me that the column is ambiguously defined. But I will specify here that it's about the students year. So students year. And I can see that all the students that are here involved in taking the grades, they are from the second year and from the third year. And they actually all the students from the second and the third year here in this table. Why I don't have any students from the first year? Just because this is the first semester when we are teaching databases, and because in the first semester the students that are in the first year didn't passed by any exam and didn't have any exams yet, and that is why they don't have any grades. But there are some students in the first year, as we could see in the table student. Those are the students. This four students are not used in the join operation. They are not used. Okay, let's check now. Let's find out what are the students that are used in the join. For example, for this one, I will do something like select everything from students, natural join, grades. So these are the students, and now I will project those answers only on the first name and the last name, and I will obtain all the students that are from the that are associated with the 42 grades there. And if I'm trying to find only distinct values here, I can write here distinct, but I will have an error here. The error is that this Jane Keller and this J Keller are different persons. If I'm writing here distinct, I will obtain only one Jane Keller in the result. Okay, let's test it out. It's only one Jane Keller and not two of them. And if I'm trying to obtain both of them, I can add here as a distinct with the registration. So those will be all my 9 students that are in the second and the third year. So these are the lines that are in the natural join. Of course, I can make the projection over all the attributes here to obtain the lines, the entire line from the table students. Year something like this. Year, group, scholarship, date of birth. Something I didn't write well. What is the description of the table students? It's group number, group and NO. Okay. So something like this. This is the table that the rows that are in the table that are used for selecting the students that are in the natural, that are used in the natural selection. So they are enough to get all those to obtain the rows that are used in the natural selection. The other rows are not important in this operation, but I can. This is actually called the semi-join, and I will tell you about semi-join in a few seconds. The other operation that I'm interested in, it's the anti-join. The anti-join is has the results the rows that are not used in the natural join. For this, it is simpler for me to do something like in SQL, select everything from students, and I'll do this minus operation that I told you about in the beginning. The expression must have the same data type as corresponding expression. So probably I will have something. I'm having here something like registration number, and I don't have here registration number, or something is different here. So I discovered what the problem was, is even though it has the same registration number field, one of them is the varchar 2 of 6 characters and the other one is a number, and this should not be possible because it's they do the conversion here, but when I'm trying to do something like the minus, they don't have the same type here and the same type here. So it's an error I did, because I should have the same registration number as being a varchar 2 of 6 characters. I will repair it and retry this command. Okay, so this is the operation for the semi-join. It actually obtained the rows from the students that are not used in the natural join. For this one, I selected all the rows in the students and I removed the rows that are used in the natural join, and I removed the rows by having registration number, last name, first name, years. Actually, the fields that are in the table students. So when I'm doing this, I obtain all the students in the first year because the one in the second and the third year are used in the natural join. Okay, this is called the anti-join. The anti-join then contains the rows from the table that are not used in the natural join. Okay, and this one here is the semi-join, contains the rows in the table that are used in the natural join. Okay, and I told you that I have this thing here, so in order not to have but now it's not a problem anymore because I have two different. I have the registration number also for the Keller join here. They're using. I'm using this thing not in order not to get it from for each mark, for each grade, to have the same student over and over again. Okay, so I have those two operations. The first one is called the semi-join, and the second one here is called the anti-join. The remaining lines from table R1 that are not used in the table in the natural join. Okay, those two operations are written here. The semi-join. The semi-join can be a left semi-join that only selects the rows from the left relation that have a correspondent as a natural join in the right relation, but they actually select only the rows from the first table, not from the second. Doesn't select anything from the second table. So it's the projection over U1 of the natural join. As we could see here, this is the projection over U1. The attributes in the relation, the first relation, are exactly the one that I selected. From the students, natural join grades. So this is the selection only of the attributes from the first relation. And if I'm looking at the anti-join here, this is obtained by having the first relation minus the semi-join that I just explained you that I obtained over there. So there are three other type of joins. This is the left outer join. The left outer join will get all the rows from the left table, but will also add the corresponding lines or the corresponding tuples from the second relation, if there are any. If there are none, then the lines from the first relation will be completed with the null value, as we will see in a few moments. So I have here select everything from students, left join grade. As we could see, there are some students that don't have any grade, and we will have null there over those fields. Left join. I have to add here a criteria. One student dot those are the lines that are only from the left table, and they don't have any association with in the right table. The other ones have also the grades that are associated with each person. The right join, it's the same, but it will get only the values from the right table of the join operation. And the full outer join, I will have all the rows even though there are no association, and where there is no association between the rows from the left table or from the rows from the right table, I will have null on those fields. For example, I will try to do something like to see each teacher what course he teaches. For this, let's describe courses, describe the teachers, profs, and I will have something like this is that's something that joins that like the join criteria is with this didactic table. I will have something like select everything from students. This is the renaming of the table students. Join full author join, but not students. I said that the courses. Full author join on chapun.id equals d.id full author join. This is what I have to do here, because there are this is the middle table involved, and I have to do two full author join. The table professors equals the dot, and as you can see here, we have the course that associated with the teacher that teaches it. Some teachers that don't have any courses associated with, for example, those, and some course that don't have any professors associated with it. So this is the full author join. It completes with null those values that don't have association from the other table. Okay, this is what I wanted you to know about the functions and operations here in relational algebra. The next course that I will teach is going to be about functional dependencies, and this uses the concept that you just learned, the one from this algebra, from this relational algebra.